Welcome to Quantum Mechanics, a journey into the microscopic revolution. This video explores the physics of reality. We begin with part 1, the collapse. We will explore why classical physics failed to explain the subatomic world. The UV catastrophe showed classical laws predicted infinite energy in blackbody radiation. Max Planck solved this by proposing that energy is, quote, quantized. Planck's constant, 6.626 times 10 to the minus 34 joule-seconds, defines the quantum scale. This fundamental number is essential for the structure of atoms and the existence of the universe. The photoelectric effect provided further proof. Albert Einstein showed light is not just a wave, but also discrete particles called photons. Niels Bohr's model proposed quantized orbits. Electrons exist in fixed energy levels and jump between them, explaining why atoms emit specific colors of light. Part 2 is wave-particle duality, the concept that fundamentally changed our understanding of matter. The double-slit experiment shows matter's weirdest trick. Particles act as waves when unobserved, creating interference, but act as tiny bullets when measured. Measurement creates reality. De Broglie envisioned that if light is a particle, then particles must be waves. Every object, including us, has a matter wavelength, though it's too small to observe in macroscopic objects. Quantum probability is characterized by randomness, the wave function psi, and observation. The wave function represents all possible states, and observation causes it to, quote, collapse into a single state. Part 3, the math, explores the essential contributions of Schrödinger and Born. The Born interpretation shows that the square of the wave function magnitude gives the probability density. Normalization ensures the total probability of finding a particle is 100%. The Schrödinger equation is the fundamental engine describing how quantum states evolve over time. It uses the Hamiltonian to represent total energy, and its solutions give us the discrete energy levels of atoms. The Heisenberg uncertainty principle reveals a fundamental limit. The more precisely you know a particle's position, the less you can know its momentum, and vice versa. This is not a measurement error, but a property of the universe. Part 4 covers the phenomena, the strange but true behaviors of the quantum world. Superposition means a system exists in all possible states simultaneously until measured. Schrödinger's cat illustrates this paradox, both dead and alive at once. Quantum tunneling allows particles to pass through impenetrable energy barriers. This phenomenon is critical for the functioning of the sun and modern electronics. Quantum entanglement is, quote, spooky action at a distance. Particles are linked so that affecting one instantly affects the other, a reality confirmed by experiments. As Richard Feynman wisely put it, if you think you understand quantum mechanics, you don't understand quantum mechanics. The Pauli exclusion principle states that two identical fermions cannot occupy the same quantum state. This rule gives atoms structure, enables chemistry, and is why matter has solidity. Part 5, the impact, shows how quantum mechanics is already in your pocket. The digital age relies on quantum mechanics. Semiconductors, transistors, and silicon chips rely on quantum band theory, making computers and the internet possible. Lasers are purely quantum devices, relying on stimulated emission, a process predicted by Einstein to amplify light. MRI technology detects the quantum spin of protons in the body to create detailed diagnostic images, allowing doctors to see soft tissue without dangerous radiation. The future lies in quantum computing. Qubits, unlike classical bits, use superposition to process data in entirely new ways, ushering in the second quantum revolution. Quantum cryptography uses entanglement to create secure encryption that is physically impossible to hack. Any attempt to eavesdrop immediately changes the code and alerts the users. The big picture is that everything is connected. Quantum mechanics explains how stars burn and how elements are created. We are only beginning to master its infinite potential. In summary, the quantum revolution has redefined reality. From matter waves to qubits, our entire world is fundamentally quantum. The key takeaways are duality, the inherent probability of the universe at its smallest scale, and the power that quantum tech holds over our modern existence. Thank you for joining this journey into quantum mechanics. Join the revolution.